thank you so much, Vincent, for presenting for us today.
No problem. Good morning, everyone. So today I'm going to be presenting on X-ray absorption spectroscopy for battery materials. So I want to first go over the basics of XAS and what it really is. So in an X-ray absorption experiment, what you're doing is basically shooting X-rays at a sample. And when this happens, since X-rays are ionizing radiation, it'll interact with the core electrons of your atoms. And in doing so, it'll basically promote or knock out a core electron into an empty state, like so. And so when this happens, your X-ray is going to be absorbed. The energy of the X-ray is gone into promoting that electron. So you can basically in an XAS experiment plot as the incoming energy of your X-ray changes, how the absorbance of the X-ray changes. So you can see in this absorbance versus energy plot, as you increase the energy of your X-ray, you get kind of a decrease in the absorbance. And this is kind of intuitively just due to the fact that the stronger the energy of your X-ray, the greater the possibility of it just not interacting with your material at all. But in addition to this broad background slope, you can see that there's kind of peaks at certain points, energy points on the x-axis. And these peaks are called what are called edges, which basically correspond to when the energy of the X-ray is strong enough to promote a core electron into an empty band. You can have a larger absorbance, and so you have an edge. And you have different kinds of edges. You can see they're labeled by letters K, L, and M. And they really just correspond to your principal quantum number. So K is n equals 1. So a K edge would be the promotion of, say, a 1s core electron into an empty state, where L would be a sort of maybe like a 2p or 2s electron. So what XAS does is it probes these core electron transitions. And in doing so, it can give very useful information such as oxidation state, geometry, local structure, and more. So going into more of the experimental setup for XAS, we basically have X-ray generator, which gets filtered into a monochromatic beam. And you shoot that beam at a sample, and you can collect data either through different modes. You can do a transmittance mode where you basically just try to detect how much X-rays have been attenuated. So you have the intensity of your initial X-rays and intensity of your outwards X-rays. So basically by using Beer's law, you can get the absorbance of it. But there's also different methods to get absorbance. For example, you can have a fluorescence mode, which basically detects secondary X-rays that are released from the sample as these electrons fall back to the core state. So what's happening here is that when you promote the electron into an empty state, eventually it'll have to drop back down and refill this hole that's been made in the core states. So there's two ways of doing this. When you back down, you release energy either as X-rays, what are called secondary X-rays, and this is the fluorescence that is detected by in the fluorescence mode. Another way that this decay happens is that the energy is released as an electron instead, and this can be detected. This is called an Auger electron, and this can also be detected in an electron detecting mode. But regardless of what your detection mode is, whether it's transmission, fluorescence, or electron, there's always a way to back out the absorbance from it. So you see a fluorescence mode, instead of having a log equation, it's just a simple fraction. So regardless of what mode you're in, your absorbance can be back calculated, and your XAS data can be interpreted in the same way. Okay. Going a bit more into experimental details, XAS is a synchrotron technique, which means that it requires a synchrotron light source. And I'll first go over what a synchrotron is and what synchrotron radiation, how synchrotron radiation is generated, and then I'll go into why exactly XAS needs this kind of synchrotron radiation to operate. So synchrotrons are basically storage rings for electrons, where electrons are being accelerated circularly very fast in a very large ring. And this generates X-rays because whenever you accelerate a charge, you result in light emission. And in this case, for synchrotrons, that light is X-rays. So the lights are the X-rays are basically generated tangential to your storage ring. And so what happens in an actual beamline, an actual synchrotron, is that you have what's called beamline stations that are tangent to your synchrotron. And in each of these stations, you can do lots of experiments with these X-rays that come out of it. So what's different
Vincent?
about, yeah.
On that last point, could you explain again why you're generating X-rays here? Like, what aspect here is acceleration?
Yeah, so the acceleration is the change in movement, right? Because acceleration is just a change of velocity. So the radial movement of the electrons is what's accelerating. And in this case, what's causing the radial movement are what's called bending magnets. You can see they're here. So these magnets are curving the electron. So when the electron path curves, it's accelerating and it generates an X-ray tangential to the curve. Does that make sense? Or is that clearer?
Yep, thank you.
Yeah. So we know how synchrotrons generate X-rays, but how is that different from lab X-rays? And why do we absolutely need synchrotron X-rays for XAS? So the reason is that XAS requires a really intense X-ray beam, or else you're not going to have your X-rays won't be able to penetrate into the sample. And also it requires a tunable X-ray source. And what I mean by that is that if we go back to the first slide, we're varying our X-ray energy. So we need to be able to vary our X-ray energy source in order to do XAS. And in the lab setting, what most of us are used to are X-ray tubes, which is basically, for example, copper K alpha generation in the Empyrean detector. And in this process, how X-ray is generated is a metal target. For example, copper is bombarded with electrons. And basically, this generates a characteristic X-ray wavelength along with a broad background emission. So if we take a look at what's actually being generated in the Empyrean on the first one of Eatings, we have a peak of intensity corresponding to copper K alphas that we're familiar with. But we also have a broad background emission. And because XAS requires a tunable spectra, only the background emission is really useful for XAS experiments. However, it is background emission, so it's so weak that we can't use it for XAS. And this is highlighted in this plot here, where we kind of have the tunability on the x-axis and the intensity, the brightness on the y-axis. And you can see that compared to lab X-ray sources, synchrotron sources are much stronger, orders of magnitude stronger, and they're much more tunable. So only really synchrotron sources work for XAS experiments. Okay. So I want to now go over how XAS is useful. So XAS is an element-specific technique. And this is because each edge corresponding to an element occurs at a specific energy range that is very far separated from any other element. So your vanadium edge and your manganese edge, for example, would be very far separated energy. So you can focus only on the range that is relevant for a vanadium edge and only look at your vanadium in your sample. So this is super useful that you can probe a specific element that you want. And in addition, XAS doesn't require a crystalline sample, because it's not probing. It could in theory probe long range order, but really it's probing short range order and electronic structures, which don't require crystal material. So this is particularly useful in the battery field for example, maybe polymer materials or very disordered materials. XAS would be a good technique to use. So I want to go over also the difference between hard and soft XAS, which basically is just a difference in between how high energy the X-rays are. And soft X-rays are basically just X-rays which have longer wavelengths and thus lower energies, so around less than 2 keV. And hard X-rays, there isn't really a clear-cut distinction between the transition, but greater than a few keV are considered hard X-rays. So you can see an example of this if we do a broad energy sweep of iron. We can see that the iron L edge, which is a 2p to 3d transition, occurs at 710 eV, so it counts as soft. And whereas the iron K edge occurs at around 7.1 keV, so that's a hard X-ray. So the soft X-rays, usually you use them for lighter elements because they have lower binding energies for the core electrons, so that you don't need as much energy to knock out those core electrons. In addition, usually higher principal quantum number edges, such as the LMN edges, are used for soft XAS. This is because as you go further away from your core, also the binding energy decreases. So soft XAS is a bit more surface sensitive. They penetrate a bit less than hard X-rays, which can actually penetrate anywhere from a few millimeters to a few centimeters, depending on your samples. Okay. Oh, my slides are out of order here. Sorry. So now that we know the experimental setup of XAS, let's go into the actual interpretation of XAS data. So basically what we have in XAS is, from kind of our raw data here, we kind of process it a little bit and basically smoothen out these two beginning and end curves so that they're flat. So we end up with something like this. And there's basically two regions of the XAS data that are interpreted and analyzed separately. So the first region is the Xanes region, which is X-ray near edge absorption structure. So near the rising edge, this is a Xanes data. And then the XAS data is the extended X-ray absorption fine structure. So it incorporates these wiggles as we go out, as we go to higher energies away from the edge energy. That's the XAS data. And each region of XAS data can tell us very different things about our material system. So Xanes is usually analyzed more qualitatively and can give things like oxidation state, local geometry, and electronic structure. Whereas XAS is usually analyzed quantitatively, and it can give information such as bond length, coordination number, and distortion. Okay, so let's focus. I'll go over both the Xanes and XAS, and let's focus first on the Xanes, which is again the near edge structure, not the wiggles that are higher energy, but the lower energy structure near the edge. So basically, the Xanes structure has what's called a edge energy, which is kind of the energy where you see this first big rising edge occur. And there's different ways to determine this energy. The most common way is to just take the peak in the first derivative. So it might be like here in this case, I'm not quite sure. Or other times people can just take the first big peak. So it would be here for this red peak, here for this blue peak, and here for this green peak. But this edge, regardless of how you get it, this edge energy can give the oxidation state of your material. Because as you can see here, as we go from manganese 2 oxide to manganese 3 oxide to manganese 2 to 3 to 4 oxide, we increase the edge energy as the oxidation state of our manganese increases. And the reason this happens is purely electrostatic in origin, because as you oxidize your material, you're removing electrons, which reduces the shielding that you have. So it'll be harder and harder to remove your electrons from the core and from the core state. So the energy needed will increase, and this is reflected by an increase in the edge energy of your XAS. So a lot of times, people will use this, especially in the battery field, to get oxidation states. You do need to be careful that you do need to have a kind of a reference sample for this edge energy, because in addition to oxidation state, this edge energy is affected by the bonding and the local chemistry around your absorbing atom. So that's our edge energy. But we also have what are called preedge peaks. So if you see down here, there's little bumps before this big large bump, and those are called preedge transitions. And so these can also give oxidation state based on where they're located, but they can also give qualitative information about the geometry and distortion around your absorbing atom. And to clarify, by absorbing atom, I mean that if you're focusing on manganese K edge, your absorbing atom would be manganese. Because remember, XAS is element specific. So more about the preedge peaks and how we interpret it. So again, the center or the centroid of the preedge peaks will increase in energy as the oxidation state of your absorbing atom increases. This is similar to the edge energy. However, we can actually tell a bit more information qualitatively based on the intensity of the preedge peaks. So the origin of the preedge peaks are from what's called bound state transitions. And these are transitions that are normally forbidden by the selection rules. So the selection rules dictates that you can only have a change in the azimuthal quantum number L by plus or minus 1. So what this means is that you can only go from an s orbital to a p orbital or a p orbital d orbital, but you can't go directly from an s to a d orbital. So because that's going from L equals 0 to L equals 2. So normally 1s to 3d transitions are forbidden. However, in these materials, you can have some 3p and 4d orbital mixing, or maybe hybridization is a more familiar word that can occur, especially when the geometry around your absorbing is distorted. So the preedge peak intensity will increase depending on what kind of geometries around your absorbing atom. So if you're in a tetrahedral environment, you'll have high mixing and thus high transitions and high preedge peaks. And if you have an octahedral environment, you'll basically just have no preedge peaks. So you can see this experimentally, where we're looking at nickel K edge zanes. And in particular, we're looking at 2 different nickel compounds, one where the nickel has a square planar geometry and one where it has an octahedral geometry. And you can see here that the square planar nickel compound has much more intense preedge peaks compared to the octahedral. So preedge can give very useful information, especially about distortion, because if your octahedral is distorted, it won't be as central symmetric, and you'll also see greater preedge peaks. Okay. So now we're gonna talk about the XAS data analysis for XAS. So the XAS again refers to these features in your spectra which are kind of undulating a bit after your rising edge, so around this area. And what's causing these wiggles is basically when your X-ray interacts and kicks out a core electron from your atom, that electron, which is basically an excited photoelectron, scatters around nearby surrounding atoms. And this scattering results in backscattered waves that can interfere either constructively or destructively with outgoing waves from your absorbing atom. So when it interferes constructively, you'll have an increase in the absorption cross-section. And when it scatters destructively, you'll have a decrease. So you can see that's the origin of these wiggles in your XAS. So there's actually probably a better way to visualize these wiggles, and that's with the Fourier transform. So what a Fourier transform does is that it, in the simplest way, it basically isolates your signal into constituent frequencies. So we have kind of a modified XAS data here, which I won't go into really how it's basic conversion from energy into inverse angstroms into K-space. But you can see kind of the XAS wiggles in the spectrum. And if we apply a Fourier transform, we'll get something that we can interpret a bit more easily. It's very similar to a paired density function where these three peaks correspond to interactions between the absorbing atom and the nearby atoms. So in this example, we have a molecule where the copper is bonded first to a carbon and then to a nitrogen and then to another copper. So this first peak would correspond to a copper-carbon bond. The second peak would correspond to a copper-nitrogen bond, and this third peak would correspond to a copper-copper bond. So by applying a Fourier transform to our XAS data, we kind of get a more intuitive sense of what the XAS can actually tell us. And what we actually do is basically, sorry, if we go back here, try to fit this spectrum to a model equation. And by fitting it to an equation, similar to Rietveld refinement, we can get important parameters such as bond length and coordination numbers. So let's go over how this actually occurs. So this is what's called the XAS equation. And don't worry, I'll break down, it's actually pretty simple. I'll break down these terms in a way that makes it kind of simple to understand why they're even here. So let's look at basically a simplified version, an idealized version of what an XAS wiggle would look like. It's basically an oscillating sine wave with an amplitude that decreases as k increases. So we of course have an amplitude term, which depends critically on your absorber scatter distance, R sub AS. And this is basically if you're talking about your nearest neighbor, RAS would just be the bond length. It also depends, is directly correlated with your coordination number, which makes sense because the more coordination you have around your absorbing atom, the more scattering you'll have. So the larger the amplitude you'll have. So in addition to an amplitude term, we also need to have an oscillatory term, which describes the wiggling of your XAS data. And this also depends on your bond length. And then we finally have a damping term, which describes how our signal attenuates over as your k increases. And this is dependent is basically a decaying exponential function, which depends on your bond length and also sigma squared, which is basically the variation in bond length. So if you have a distorted octahedra, the sigma squared will be larger. So And then we sum over all the scattering paths in your material. So basically, the key, by fitting this equation, which simulates your XAS data to the actual observed XAS data, we can get out three important parameters. We can get out the absorber scatter distance, the coordination number, and the variation bond length. It's important to know that because of this dampening effect, only a few coordination spheres are captured by the XAS. So once you get out to like the fourth nearest neighbor or the fifth nearest neighbor, they really have no effect on the XAS data. And because of this, XF is known as a local structure probe, and similar to NMR in that way. Okay,
Vincent,
so yeah.
on that last point, I think it was interesting how you talked about how XAFs is similar to a pair distribution function. For context, pair distribution function basically is a way to handle diffraction data that will allow you to see distances much in the same way here. Why would you want to use a pair distribution function versus XAFs to characterize structure in general?
That's a great question. And the main reason is that a pair distribution function gives the actual pair distributions. So when I say it's like a pair distribution function, it's not what I mean is it's not exactly it, because even though this is like centered, I say, at around 1.5 angstroms, right? This doesn't actually mean that your copper-carbon bond is 1.5 angstroms, because notice that there's a phase shift due to some scattering effects and interference effects. So it doesn't actually give you that separation. So it's not as accurate as PDF. It's actually not really accurate unless you fit it. But fitting and then you'll get, you'll be able to resolve this issue. But fitting is just pretty complicated for XAS. And if you don't want to deal with fitting, from personal experience, you probably don't want, if you can choose not to deal with trying to fit XAS data, don't do it. And a PDF would just be a much simpler way of trying to get that distance.
Okay, interesting. Yeah, the other factor too is that this is element specific too, right? So
yeah,
whereas PDF won't be.
That's true. So I guess PDF has its own, I guess I've never done PDF, but you will probably run into some problems trying to actually identify what each peak in the PDF is, but there's pretty good ways of like simulating PDFs, right? So you can attribute them pretty well, I'm assuming.
Yeah.
Okay, so yeah. It might be a benefit for this to be element specific, but yeah.
Cool, thank you.
Okay. So now I've gone over pretty much the basics of XAS data, how it's split into a Zane spectra and a XAS spectra, and what data we can get from each different part of the XAS spectra and how it's interpreted. So now I want to go to a case study. So this paper, basically what they did was they performed operando XAS on standard nickel manganese oxide cathodes. And you'll see that they really kind of can get a lot out from this XAS data. So what I mean by operando XAS is that they're running XAS measurements as the battery is charging. So I'm going to give a brief overview on the experimental setup because an operando setup requires more specialized equipment. So in this case, they basically have a specialized battery, except that you need X-ray transparent windows for your XAS experiment to be effective. So basically, they have low Z windows, either kind of organic polymer-based windows or beryllium windows, which X-rays can basically transmit through. And they charge the battery. As they charge the battery, they run the XAS experiment by shooting the X-rays kind of perpendicular to it. And they basically take several scans as a function of time, so as a function of your charging, of your battery charge state. So what kind of information do they get out of it? So first, let's take a look at the Zane spectrum, again, the near edge spectrum. So you can see, especially in the nickel KEH Zanes, it's much clearer that as you increase in your scan number, which means that as you're charging your battery, your edge energy shift to higher energies, which indicates that your nickel oxidation state is increasing. But also, or actually more, in this study, they actually prefer to use the change in position of the pre-edge peaks in order to determine oxidation states. This is because manganese, you can see it has kind of this weird rising edge structure, which you can't tell if the oxidation state is increasing because it's going this way or decreasing this way or staying the same. So pre-edge peaks don't have that kind of problem. So they actually analyze the pre-edge peaks instead in terms of trying to determine whether the oxidation state increases or decreases or stays the same. So you can see here in this left plot that they plot as a function of your charge how the peak position of the pre-edge changes. And we can see here that only the nickel peak position increases on charge. The manganese stays pretty much the same in terms of your peak position. So what this means is that in this nickel manganese material, you only have nickel redox, while your manganese 4+ ions are redox inactive. So that's pretty useful information about your battery material. Another thing, so remember that in addition to the position of your peak, the intensity of your pre-edge peak will give you information about the local distortion. So the more intense your peak is, the more distorted it is. The local structure around your absorbing atom is. Oh, I should clarify that they did both manganese KEH and nickel KEH experiments on it. So they probed the absorbance around both of the manganese and nickel ions. So if we look at the peak intensity trends, we can see that both the manganese and the nickel atoms show more distortion on charging. So that's useful qualitative structural information to know. But in addition to the near edge structure, they also did quantitative fitting of the XAS structure, and they were able to get bond lengths of your nickel around your nickel and how those bond lengths vary as a function of charge. And they actually did a pretty cool study here where they use this bond length change to figure out how the charge compensation effects in this material. And what I mean by that is that when nickel 2+ is oxidized to nickel 4+, how is it actually oxidized? Is it oxidized in one step from nickel 2+ directly to nickel 4+, or does it go from nickel 2+ to 3+ to 4+ instead? And what they did was, first, you can model how you expect the bond lengths to change based on which process. So this solid line, so in this plot, basically you have your bond lengths as a function, or your coordination number as a function of your charge state. So for nickel 2+ directly to nickel 4+, you expect a trend, which is this solid line. And for the nickel 2+ to 3+ to 4+, you expect the dotted line. So this is what they modeled. Their expected coordination number versus charging to look like. And sorry, when I said bond length, you can extract both bond length and coordination number. So they basically, you have different kind of a short and a long bond in nickel ions. So for each bond length, they can extract the coordination number. So experimentally, you can see these data points here. Of the coordination number versus your charging, and you can see that it matches more closely the dotted line, which means that most likely in this material, you have nickel oxidizing from 2 plus to 3 plus, and then 3 plus to 4 plus, rather than a one step from nickel to 2 plus to 4 plus. So this is just a pretty cool demonstration of how powerful XAS is. You can get the charge compensation mechanisms by quantitatively fitting your XAS data to get coordination number and bond length. So as a summary, XAS can give a lot of data about your structure and about your oxidation state. Xanes can give your oxidation state. Preedge can give both oxidation state and qualitative information about your local distortion. And XAS can give local structure information such as coordination number, bond length, and bond length distributions. However, there's a lot of variation in XAS techniques. There's like soft XAS, which I haven't covered. There's a lot of tricks you can do with XAS. So there's actually, a lot more that you can get from XAS, which I can't cover just in this presentation. So if you're interested, this paper is super useful, is super informative about XAS techniques and how they can be applied specifically to battery materials. So if you're curious, I suggest you check it out. So yeah. So thank you, everyone.
Thank you, Vincent. Thank you. That was wonderful. Questions? Anybody, please feel free to speak up and unmute yourself and send in your question.
Hi, Vincent. Great explanation of XAS. I was wondering, what's the origin of the names L, M, and K edge? Like, do they refer to something in particular?
Yeah. So let's see. So they basically refer to, I don't know why they're called L, M, or K, but they basically refer to which core electron is being excited by the X-ray. So K edge, if you have a K edge, it refers to the 1s electron being excited. We can also have different core electrons, right? You can have 2p or 2s core electrons being excited. So L refers to if the core electron has a principal quantum number of 2. So 2p, 2s. And M is if it's 3, if your principal quantum number is 3. So 3d, 3p, 3s. It's basically which kind of core electron is being excited. That's what the KLM describes.
Thank you.
The splitting, the tiny little splittings like this L1, L2, L3 is just like 2s, 2p, 2d.
Yes. So in this one, it would be 2s, and then I think L1 is 2s, and L2 and L3 are both 2p orbitals that have been split. So different, they both refer to 2p, but different 2p orbitals.
Any other questions?
Sorry, I do have a question about the in-situ measurement in general, like for battery research.
Yeah.
So when you do the measurement, do you do a like holding, or like you just continue charge it or discharge it? We will do the measurement.
So I believe in for XAS, I know we just continuously charge and discharge it. It depends what you want, right? But if you're doing operando, you want to do it without holding it because you're trying to probe really what's going on as the device is running, right? Because if you hold it, then the structure might change, what the process is going on in the material might change, so you're not actually, getting the operando study. It's more of an in situ study rather than operando.
Yeah.
So for operando,
Okay. So basically, we are getting the average oxidation state at that range, right?
Yeah. But these are pretty fast. So yeah, there is like still structure change as you're doing the measurement, but on the time scale of the measurement, it's good. It's okay.
Okay. Thank you.
So I imagine for the experiments that you're showing here, they probably charged it somewhere, took it off the charging, and then put it on the beamline and then went back.
No, so this is purely operando. So while it's charging, they just run the experiment. Right. So
they called it in situ. That's what I was
because yeah, they called it in situ because what I feel like in literature, in situ and operando are pretty kind of mixed up a lot. Like we took in Raphael's class where she like really stressed what operando versus in situ was, but I found that in literature they don't abide by those rules as much. So this should be operando.
Cool. I've got a question too. So if I'm a graduate student or even an undergrad, and I'm really interested in getting some XAS done on some materials that I'm studying, what's the process I need to go through in order to get some XAS done?
Yeah, that's a great question. So remember that XAS is a synchrotron technique. So it's not as simple as, you know, XRD or XPS where we can just do it in the lab. We need to basically, these synchrotron facilities, you'll need to apply for time on these synchrotron facilities. And the way you do so is by writing a proposal or submitting a proposal to these synchrotron facilities. So the Argonne National Lab has the Advanced Photon Source, APS, where you can submit your proposals to. You can also do it at SLAC at Stanford. So basically, these beamlines are open for public research use. They'll dedicate time to you. You don't need to pay for the time there, but you do need to write a proposal, let them know why you want to do it and why it's useful, and have their proposal be accepted. And then you can run your beamline experiments at Argonne, at Stanford for free.
Cool, thank you.
Yeah. The proposal submission process, I mean, if you're interested about it, you can always ask me or your grad student mentor and talk to your PI about it. Yeah.
Yeah. They're very specialized locations, these synchrotrons, but there's a good amount of them throughout the US. So I think a lot of us here in California, and we have two in California, one at Berkeley, the Advanced Light Source, and then one at Stanford, the Stanfordtron synchrotron, or the Stanford
Synchrotron
radiation source, SSRO.
Yeah.
Cool. All right. Any other questions?
Yeah, one thing to add on that, you need to know the energy range you need, since different synchrotron will have different energy range.
Yeah. So the Stanford, which one is it? Where? The Stanford, sorry, the ALS can only do soft X-rays. It can only do low energy X-ray experiments. It doesn't have hard X-ray capability. Yeah. So when you go to the sites, you'll see basically a beamline registry where it lists each beamline. And then of course, besides XAS, there's like a bunch of other X-ray techniques, but look at the XAS beamlines, look at the specifications, what energy range can it run to? And you have to make sure that it'll match whatever edge that you want to do, right? So so ALS only really does below like soft XAS, so around this region. So you can't do that you can't do hard XAS there. All right, any more questions?
I had a small one. Do you have an idea of the detection limits for light elements, like fluorine, for example?
Yes, well, no, but I can talk about it. So this is where the mode comes into play. So transmission, you do need a fairly concentrated sample in order to do transmission experiments. If you have very dilute samples, I just know that fluorescence and electron-based modes are more sensitive than transmittance modes. So if you have a very dilute sample, which people mostly use fluorescence, yeah. So it should probably be pretty. I don't have any numerical answers, but they should be pretty sensitive if you go into fluorescence or electron receiving mode.
Okay. And so in fluorescence mode, I guess you don't have that much information on the bulk of a system, right?
Yes.
It would be just the subsurface or
yes.
surface.
Yeah.
Okay, thanks.
The electron mode is, I think, also as sensitive for fluorescence, but it is bulk sensitive, more bulk sensitive for fluorescence.
Okay, thanks.
All right.
Okay. All right. Well, thank you so much, Vincent, for that wonderful presentation. I'm going to cut off the